All right, now that we've seen what an isomorphism is and how to find or prove that something is isomorphic, let's look at what happens to basis elements of our subspaces under an isomorphism. So let's look at mapping bases here. Okay, so let's say we have T from V to W. And first, let's just say, let's say if T is 1-to-1 here, then if we have a basis, let's say V1 through VK is a basis for V, then this implies that T of V1 through T of VK, well, let's not say a basis. Let's just say linearly independent for now, because we're only looking at an injection. Let's say, so if we have is linearly independent in V, then this implies that the image of this linear independent set is also linearly independent. So this is linearly independent in W, okay? And really this is a theorem here. Now, this is what happens if you have an injection from V to W, then your linearly independent set, the image of this linearly independent set is also linearly independent, right? Meaning pairwise that their dot product is 0. Well, what if we have an isomorphism? Here's another theorem. T is an isomorphism if and only if when we have a basis V1 through VK is a basis of V, this implies that T of V1 through T of VK is a basis for W, okay? And so one way to think about this is we have an isomorphism if and only if the linear transformation takes a basis to a basis in the mapping here. So what would this look like, right? I mean, well, schematically, let's say we have a subspace V, some other subspace W, and then we have an isomorphism between them, T, right? Well, what we have is some basis, V1 through VK, right? So like V1, maybe V2, V3, et cetera, all the way through VK. If this is an isomorphism, and only if this is an isomorphism, does this collection of vectors, this basis, does this get carried to a basis for W? So then over here, you know, we could have like T of V1, T of V2, blah, 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 up through T of VK, where this is also a basis, right? Meaning these vectors are linearly independent, which we're guaranteed that they're linearly independent because an isomorphism is injective, and we have this following theorem for injectivity, and that it's a spanning set, right? So with this in mind, let's think about what we could deduce from this. Well, if an isomorphism carries a basis of V to a basis of W, well, then that means the number of elements of the basis of V are the same as the number of elements of the basis of W. But what do the number of elements of a basis define? That defines the dimension of the subspace you're in. So we have the following theorem then. Let's say V and W are two isomorphic subspaces in Rn. So with V isomorphic to W. Well, let's say V is isomorphic to W if and only if, we can say something even stronger here. So V is isomorphic to W if and only if the dimension of V is the same as the dimension of W, right? And this is really just kind of rewording this last theorem here, because if it's an isomorphism, if and only if it carries a basis to a basis, well, then V and W are isomorphic, means there's an isomorphism between them. And the dimension of V being the dimension of W means the number of basis elements are the same, right? So this is really kind of rewording this previous theorem. This theorem is in the language of linear transformations. This theorem is in the language of subspaces, right? Here, the emphasis is the isomorphism, the map itself, and the basis elements. But here, the emphasis is the isomorphic subspaces and the dimensions of these being the same. So what does this mean, right? Well, if we would think about this as a part one, then a part two would be like a moreover. This means any linear map between isomorphic subspaces. So let's say T from V to W is an isomorphism. Okay, so if you can construct a linear map, say you have two subspaces of the same dimension, if you can construct a linear map between them, well, then that's an isomorphism, which really just means we're taking one subspace and kind of deforming it into the other subspace, right? An isomorphism is really just kind of spatially or geometrically what it's doing is it's taking your subspace and it's deforming it into another subspace, right? Okay, well, let's look at an explicit example here. Let's show that V, which is R3, and W, which is the span of the following vectors, 1, 2, 1, 1, 0, 1, 0, 1, and 1, 1, 2, 0 are isomorphic. Okay, well, to show that they're isomorphic, it's a one-line proof, right? What's the dimension of R3? Well, that's 3, but how many elements do we have in the spanning set of W, right? All of those are linearly independent, and so this is also the dimension of W. This means R3 is isomorphic to W by previous theorem. So that's easy, right? To show that they're isomorphic, you can be pretty clever with some of these theorems. Just call on one of these theorems, but it's more useful and much more practical to construct an explicit isomorphism. So let's construct an explicit isomorphism T from R3 to W, right? How would we do this? Well, what's our previous theorem say? We know that it's an isomorphism. And so it's an isomorphism if and only if it takes basis elements to basis elements. So if we want to explicitly construct an isomorphism, what does that mean to construct this explicitly? That means we're trying to find the matrix A that represents this isomorphism, right? So i.e. find A such that T of X equals AX, right? That's what we're trying to do here. Well, if we know T takes basis elements to basis elements, since it's an isomorphism, that means T of 1, 0, 0 should be, right? The first basis element of V or R3 should be mapped to the first basis element of W, which is 1, 2, 1, 1. So 1, 2, 1, 1. Then we have the second basis element of R3, which is 0, 1, 0, right? Because here, what am I looking at? I'm looking at the standard basis of R3, which is 1, 0, 0, 0, 1, 0, 0, 0, 1, right? And I'm mapping them element-wise to the basis elements of W. So T of 0, 1, 0 should be 0, 1, 0, 1. And then T of 0, 0, 1 should be 1, 1, 2, 0. Cool. Now, how did we find the explicit matrix of a linear transformation, right? If you'll remember, A is given by the column vectors T of E1, T of E2, T of E3. You augment all of the column vectors that are the image of your basis elements of the domain, right? You look at the basis elements in the domain, which is R3 in this case. You look at the result or the image of these basis elements, and then the matrix representing this transformation is augmenting all of these images. And so what does that matrix look like in this particular case? Well, then we have the matrices 1, 2, 1, 1, 0, 1, 0, 1, and 1, 1, 2, 0. So this matrix A is explicitly describing the isomorphism between three-dimensional Euclidean space and W here. Great. So what if we were to construct an isomorphism more generally? Like, let's say we didn't understand how T behaves on the basis elements, but let's look at an example. Let's look at the same example, but now let's say T is understood or defined on not necessarily basis elements, right? Well, then we have, let's say T of 1, 1, 0 is 1, 2, 1, 1. T of 0, 1, 1 is 0, 1, 0, 1. T of 1, 1, 1 is 1, 1, 2, 0, right? And this is a different map, okay? But what we're trying to do is say, well, how can we find the matrix or this explicit construction based on maybe a differently defined basis here, right? This is a different different basis that we're looking at, but we still want to be able to find the explicit matrix for this isomorphism when it's not necessarily like just our standard normal basis here. So what we do is we set up A times, now you take all the column vectors in the domain. So that's going to be first 1, 1, 0, and then 0, 1, 1, and then 1, 1, 1 for the third one. And this is going to be equal to 1, 2, 1, 1, 0, 1, 0, 1, and then 1, 1, 2, 0, right? We're doing the same thing here, like you can picture on the right-hand side of A here, I have this times like I3, right? We're doing the same thing, but now this isn't I3, it's a more complicated matrix. Well, to find A, this is simple matrix arithmetic. We multiply both sides by the inverse of the matrix composed of the elements in the domain that we're going to map here, right? And so this would be A is equal to, and then 1, 2, 1, 1, 0, 1, 0, 1, 1, 1, 2, 0 times this matrix inverse. So we had like 1, 1, 0, 0, 1, 1, 1, 1, 1 inverse, right? And then this yields, I'll leave the matrix multiplication, it's fairly standard. You get 1, 0, 2, negative 1, 0, 2, negative 1, 2, and 0, negative 1, 1, negative 1, right? And so you can find the matrix for these maps in a more general setting, right? Where these aren't necessarily like basis elements, they're just elements, but you know how they're mapped. Well, to find the matrix, you still just set up this product here and then solve for A. Okay. All right. So now that we've looked at mapping bases, or how the image of a basis is a basis under an isomorphism, let's take a different like a slight detour here and discuss the kernel and image of linear transformations. So we're going to look at the kernel and image of linear transformations here. So let's recall these definitions. We've defined them before. So let's say T from V to W is a linear transformation where V and W are subspaces of Rn. Then let's recall the following definitions. We have that the kernel of T is defined to be those elements V in V such that when you apply the transformation to V, you get the 0 vector, right? So really this should be like vector V here. So remember, the kernel is everything that gets mapped to 0. What about the image? Well, the image is everything that gets mapped to by something. So this would be W in W such that for some, for some V in V, we have that W equals T of V. This is the image, right? It's the collection of everything that was mapped to under the linear transformation T. And we've seen the following theorem, but I'll remind us. So the theorem says that the kernel of T, well, I don't think we have seen this because I'd like to prove it. So theorem, the kernel of a linear transformation in W is a subspace. And the image of T, which is in the codomain, is also a subspace. Okay, how could we prove this? Well, we'll have to recall the subspace criteria. Remember the subspace criteria, or to show, let's just write this in general, like abstract, right? Let's kind of recall. To show that U is a subspace of V, we need to show that for all U1 and U2 inside of U, well, then the linear combination AU1 plus BU2 is also in U, right? If we can show this for every element, and this is for A, B scalars, right? It's very similar to this linearity property. If we can show that linear combinations of vectors in a given subset remain in that subset, well, then it's actually a subspace, right? And so this is what we need to show. So this is what we want to show for both the kernel and the image. Let's show it for the kernel. So proof. Well, I already wrote proof. Okay, to show this for the kernel, right? Let's take two elements, V1 and V2 in the kernel of T. What does it mean for two elements to be in the kernel of T? Well, this means that T of V1 is equal to 0 and T of V2 is equal to 0. Now, what do we need to show? We need to show that a linear combination of these two elements remains in the kernel. So that means we need to calculate T of AV1 plus BV2. Okay, so we have T AV1 plus BV2. Well, T is a linear transformation, which means we can write this as A TV1 plus B TV2, which is A times 0 because V1 is in the kernel of T, plus B times 0 because V2 is in the kernel of T, which is 0 plus 0, which is 0. So therefore, A V1 plus B V2 is also an element of the kernel of T. And that shows that it's a subspace of W, right? Because we're pulling vectors from W. Let's show, so that was the first one. Now let's prove that the image is a subspace. Well, let's let V1 and V2, well, sorry, how about W1 and W2? Let's let these be elements of the image of T. Well, then that means there exists V1 and V2 in V such that T of V1 equals W1 and T of V2 equals W2, right? Well, then what we need to look at is we need to look at A W1 plus B W2. And we can see immediately that this is going to be, T of A V1. Well, let's write it more explicitly. This will be A times T of V1, right? Because W1 is in the image, plus B T V2, since W2 is in the image. And then by the linearity property of linear transformation, this is TA V1 plus B V2. And so we found an element in the domain which maps to A W1 plus B W2. And so this would be our proof here that the image is also a subspace. Okay, let's next look at an example of, well, we know now that the kernel and the image are subspaces of the domain and the codomain respectively. But how would we find these subspaces explicitly, right? Well, to find a subspace explicitly, normally what we do is we write it as a spanning set, or we construct a basis, right? And sometimes those can be thought of interchangeably. So let's look at an example of how we could find a basis for the kernel and image of a map. So let's find a basis for, let's say, kernel of T and image of T, where T is a map from R4 to R2, right? And so not an isomorphism because the dimension of the domain and codomain are different. So where T is given by T of A, B, C, D is mapped to A minus B and C plus D. Okay, well, first to find a basis, let's see if we can find just how to describe the kernel as a set, right? When we define the definition that I've given for the kernel and image, these are defined as sets, right? And so let's figure out how to express the kernel and image of this particular map as a set. Well, what's the kernel? The kernel of a map are all those vectors A, B, C, and D in R4 such that they're mapped to 0, right? i.e. A minus B and C plus D is equal to 0, 0, right? This is how we would describe the kernel of this linear transformation as a set. Now let's see if we can find a basis for it. Well, to find a basis for it, let's play around with the restriction that's been imposed on the kernel, right? What stands out here is the restriction that A minus B is equal to 0 and C plus D is equal to 0. So we have A minus B is equal to 0, which implies A equals B. Then we have C plus D is equal to 0, which implies C equals negative D. Now, if we give these parameters, let's say T for A and S for C, then we can rewrite the kernel slightly. The kernel of T is the set of all vectors T, T, S, negative S in R4, and then if you wanted to be really precise, such that T and S are in R, right? The kernel is a collection of all of these vectors. Well, we can write this as T times 1, 1, 0, 0 plus S times 0, 0, 1, negative 1. And now we've found a basis for the kernel, right? Or a spanning set. And these are clearly linearly independent, so it's a basis, right? Because every element in the kernel can be expressed as a linear combination of these two vectors. And so what we've just found is that kernel of T is defined, or not defined, but has been calculated to be the span of the vectors 1, 1, 0, 0 and 0, 0, 1, negative 1. Right? And so we found a basis. The basis consists of those two elements. Cool. What about for the image? Well, the image of T is just going to be that collection of vectors such that A minus, or sorry, it's just going to be the collection of vectors A minus B and C plus D, right? Any vector in R2 that can be expressed this way is in the image here. Well, how can we write this? We can write this, the image here, as A times 1, 0 plus B times negative 1, 0 plus C times 0, 1 plus D times 0, 1. And you'll notice all four of these vectors here, of four of them, only two are linearly independent, right? Namely 1, 0 and 0, 1. And so for this reason, we have that the image of T is the span of 1, 0 and 0, 1, because those were the only two that were linearly independent, right? Which means then that the image is just isomorphic to R2 here. Cool. So what have we found here? And you may notice the dimension of the kernel of T in this case was 2, and the dimension of the image of T in this case was 2. And this turned out to be 4, which is the same as the dimension of R4, or of the domain, right? And that's not a mistake. We have the following theorem. Let's say T is a linear transformation from V to W with the dimension of the domain being M. Then the dimension of the kernel of T plus the dimension of the image of T is equal to M. Okay, so we have this following theorem. And you can see an immediate corollary of this is that the dimension of the kernel and the image are necessarily less than or equal to the dimension of the domain, right? So in certain contexts, knowing these facts can be important. So I'll record them here. Okay. Now, I want to make one more remark here about the dimension of the kernel. Let's think about the dimension of the kernel. Well, let's look at when T is 1 to 1 or an iso, but primarily when T is 1 to 1. Remember, when T is 1 to 1, we have the following condition. So T being 1 to 1, if and only if T of X equals 0 implies that X equals 0, right? So what does this mean? What this means, this criteria right here is saying when T is injective, the kernel has one element, right? Stated more properly, we have the following theorem. T is injective, right, or 1 to 1, if and only if the kernel of T is just the 0 vector, right? So the kernel is 0 dimensional in that case, right? Because you just have it's a point, right? Your kernel is one point and it's the origin, and a point is a 0 dimensional subspace, right? Okay, so I think this is all I would like to talk about for the kernel and image thus far. I think where we'll go from here is we'll explore a little more, maybe a few more, maybe quote unquote more complicated properties of the matrix of a linear transformation. And then from here, we're going to review our complex numbers so that we can start talking about spectral theory.